Okay, welcome to fourth video of Analog Electronics Lab. Okay, in the first experiment of this video, so we are asked to design and demonstrate a voltage buffer circuit for a load of 680 ohms, uh, and it has to give maximum swing. So it should utilize the maximum available swing. So maximum available swing here is 4.5 volts that is specified. The VCC given is 5 volts. This is what we are looking at. So design specifications are, we are asked to design a voltage buffer. The RE, that is the load resistance, is 680 ohms. The supply voltage VCC is 5 volt. The output swing, the maximum output swing is 4.5 volt. And we are assuming the parameters here. The current gain of the amplifier, the transistor, we are assuming it to be 100, and the reverse saturation current of the transistor is 1 into 10 power minus 13 ampere. So this is what we are looking at, the output swing. So this is 0 to VCC. So assuming 0.5 volt to keep this transistor in saturation. So out of 0 to 5, we left out with 4.5. The midpoint of this 4.5 happens to be 2.25 here from this 0. If you take it from this point, it is 2.75. So at this point it is 2.75. So V is the voltage across the resistor Re, so which has to be 2.25. That's what corresponds to this. So since V is 2.25 for a gain of for a swing of 4.5 volts, we know that since V is given by I into Re, which should be 2.25. So with the value of Re as 680 ohms, the emitter current, which is approximately equal to the collector current, will be 3.3 milliamperes. This is a circuit diagram what we are supposed to design. So value of Re is given. We are asked to find, we should find out what is R1, R2, so that we can able to get a gain of, we can able to get a voltage buffer with gain less than 1, and the maximum swing can be 4.5 volts. So now it's necessary to find out the value of R1, R2, so that we have a current of 3.3 milliampere flowing through the transistor. So this is what the expression now we have. So in order to find, in order to get a current of 3.3 milliamperes, we know that VB expression is given by Vt natural log of Ic by Is, which will be 629 millivolts or 0.629 volts. So this is the base to emitter voltage, but the voltage at the base, which is over here, the Vx is given by Vbe plus Ve. Since we know that V is 2.25, Vb required is 629 millivolts. So overall Vx becomes 2.87. So we also know from the equation Vx is given by, so as we know, if we assume that the current flowing through this R1, R2 is I1, neglecting the current flowing through the base, so then Vx is also given by I1 into R2. So that's what is given here. So Vx is also given by I1 into R2. So we are assuming I1 to be 10 times of IB. So where IB is given by IC by beta. So we are going to get a current of I1 as 330 microampere. So from which we can get the value of R2 as 8.69 kilo ohms. So we know that R1 plus R2 is given by VCC by I. So from which we can get the value of R1 as well as R2 as 15.15 kilo ohms. So since we know the value of R2 and R1 plus R2, from which we can easily find out what is the value of R1. So R1 value happens to be 6.46 kilo ohms. So these are the design values of R1, R2 and Re. Of course, we are using a coupling capacitor of 0.1 microfarad. So this is the design values are 6.46, this is 8.69, this is 680, C is 0.1 microfarad. We should choose the nearest possible values for the components. For R1 we can use 6.8, for R2 we can use 8.6, Re can be 680, ohms and CC is 0.4 microfarad. So once we make these connections using these resistors, so we have to check the DC value at the emitter terminal. So if it is other than 2.25, so we are expecting a current of 3.3 milliamperes with these values of resistors connected. And if we are getting 2.25 or very close to that, then the circuit is fine. Otherwise, we have to change the value of R1 or R2 so that the voltage across the resistor RE happens to be 2.25. So we should vary R1 R2 such that V becomes 2.25. So once we are through with that, we can actually find out what is the gain of the amplifier. So we know that VCC is 5 volts and VT is equal to 26 millivolts, which is the thermal voltage. We have to measure what is the voltage across the resistor RE, and by which we can find the value of collector current, which is approximately equal to emitter current. Given the basic equation, V by RE happens to be IE, which is approximately equal to the collector current. We can get the expression for a value of GM using this expression, IC by VT, and we can ultimately find what is the gain of the amplifier, which is gained by GM into RE by 1 plus GM RE, which is always less than 1. So now this is another amplifier. Design a C amplifier and find and verify the mid-band gain of 25 dB. Also demonstrate its frequency response. So we are asked to design a C amplifier for 25 dB gain, and we are also asked to demonstrate the frequency response. So we have to change the frequency of the input signal from a low frequency to high frequency. We have to see how does the output changes. So specifications are gain is 25 dB, the collector current is 1 milliampere, the voltage is 5 volt supply voltage, and these are the assumptions. Now this is the circuit what we are having. So now you can see we have R1, R2, there is a RC, and we have a RE, which is having a pot here. Now this is this connection is used so that we can get the desired gain of 25 dB. We know the design equations, so we shall assume that VC, the voltage, the collector is half of VCC, so that we get a better swing. So that the VC becomes half of VCC, which is 2.5. So assuming a current of IC of 1 milliampere, the RC becomes 2.5 kilo ohms. For an IC of 1 milliampere, so we know that VB should be almost close to 600 millivolts. And assuming a voltage drop of 100 millivolt across RE, so which is nothing but VE is equal to 100 millivolt. So naturally the voltage at the base terminal, which is over here, happens to be VB plus VE, which happens to be close to 700 millivolt. So using these assumptions, we can get the value of R1 plus R2 as 50 kilo ohms, and we know that Vx is equal to 0.698 volts, and we know the value of I1 to be 10 times of IB, which is 100 microampere. So we can actually find out what is the value of R2. So R2 is 6.98. So naturally the value of R1 comes out to be 63.02 kilo ohms. And we know that VE is assumed to be 100 millivolts, which is gained by I into RE. So from which you can get RE as 100 ohm. So we are using a 100 ohm part so that we can get the desired gain. So now we are using RC of 2.2 kilo ohms, which is very close to the standard, which is the standard value, and it is close to 2.5 kilo ohms, what is designed for half of VCC as our collector voltage. Now you can see we know the expression for AB is given by GM into RC divided by 1 plus GM into RE dash. So this RE dash is that part of the emitter resistor which is not bypassed by the capacitor CE. So here we have the entire resistor is RE. You can see now this emitter capacitor is actually bypassing some portion of RE, and it is not bypassing some portion of RE. This RE dash is that portion of RE, that is emitter resistor, which is not bypassed. So in the expression for the AV, it is Gm into RC divided by 1 plus Gm into RE dash. RE dash is the value of the emitter resistance which is not bypassed by the emitter bypass capacitor. So that's what is this RE dash. So to have a gain of 25 dB, which happens to be 17.8 volt per volt, so with the GM as 1 over 26 ohm inverse, the AV is supposed to be 17.8. In order to get the AV of 17.8 and with the RC as 2.2 kilo ohms, so RE dash should be 97.5. So meaning out of 100 ohm, so it should not be bypassing almost 97.5 ohms should not be bypassed, meaning the part should be at the lowermost position so that the entire resistance of this RE is not bypassed. So if we keep it at the top, most of the resistance is bypassed so that we get maximum gain. So we actually found out what is the value of RE dash. It is found out to be 97.5 ohms. So using these values which are nearest to the available design values, so R1 has 47K and R2 has 6.8, RE has 100 ohm part, and the coupling capacitor has 0.1 microfarad and the emitter bypass resistor has 47 microfarad, and this RC is actually 2.2 kilo ohms. So we have to actually verify the circuit whether the collector voltage is close to 2.5 or not. If it is not 2.5, we may have to slightly adjust the R2 and we have to change the value of RE so that it is close to 97.5 and we get again a AV is equal to 25 dBs. So once we are done with that, we can actually sweep the frequency from a low frequency to high frequency, maybe from 10 Hz to 10 megahertz. So once we sweep the frequency using network analyzer, it sweeps from a low frequency to high frequency. At lower frequencies, it is upon increasing that it becomes constant in midband and it again reduces. We know that this is increasing due to the Rin and Cc. So we can actually find out what is F1, which is 3 dB down from the maximum point, and similarly we can find F2, which is 1 over 2 pi R out into C out. So in this case, R out is Cc, C out is the base to collector. So this is the Miller capacitance of this capacitance. Now we have this base and collector. So this base to collector capacitor, that is CBC, can be represented on either side of the output as well as input using Miller Miller effect. So that's what we write the C out as 1 plus 1 over AV into CBC. So we can actually find out what is this frequency, 3 dB down from the maximum. F2, it's again 3 dB down from the maximum. So after finding out these frequencies, we can actually verify that using this equation, and we can also actually estimate what is the value of C out, because we know everything except C out. We can actually find out what is the junction capacitance of the transistor. These are the readings to be taken. PC, we can find out what is IC, the transconductance, we can verify the theoretical and the practical GM. Now AV is not exactly GM into RC, it's actually GM into RC divided by 1 plus GM RE dash, because RE dash is not totally bypassed. The entire emitter resistor is not totally bypassed.